I'm here to talk about manure management for this fundamentals course. So when applying nutrients to the land to grow crops, there are several options. Legumes add nitrogen, biosolids, which you're going to talk about today, commercial fertilizer, but we're going to talk about manure. There's a lot of benefits to manure application to a soil. It improves organic matter content, which also helps increase the CEC, the cation exchange capacity, water holding. It improves the structure, how well that soil holds together. It can lower the bulk density. It can also increase microbe activity. It helps recycle nutrients between animals, soils, and crops. So if you're feeding that corn to a cow and then you can use manure from the cow to apply as a nutrients, you can actually cycle the nutrients within that system. So it's a natural resource. It doesn't have to be created synthetically like commercial fertilizers. So you can reduce the money you would spend on commercial fertilizer, and you also reduce the energy to create commercial fertilizer. To create nitrogen, we actually have to use petroleum. It has its risks. That's why you're in here. That's why you're in a nutrient management class. That's why you want to be nutrient management advisors. If you don't understand how to apply these nutrients, you can actually cause excess nutrients in our ground and surface water. But manure could contain pathogens. It could contain heavy metals and volatile organic compounds and pharmaceuticals and antibiotics. But we're really concerned with excess nutrients. It can also lower the air quality. You have the smell of ammonia, sulfur, and methane. That's more of a local complaint. And you can create greenhouse gases from it. Now, this was a picture the old advisor had in here. So land application of manure, the nutrient availability. Manure is usually managed to provide the three major plant nutrients: nitrogen, phosphorus, and potassium, NPK. There are also micronutrients in manure. That's another great reason to use it. When properly managed, all of the risk can be minimized, meaning you know how much is going to be available, you know how much the crop is going to uptake. You won't have excess that runs off as long as you're managing it. Phosphorus and potassium are considered to be available. And what's in the manure is going to be available to the crops. So whatever you measure, when you send it off to the lab, whatever the phosphorus and potassium is in there, it will be available to the crop. The problem with nitrogen is it can go through several different phases. It can be a gas, it can be a solid, it can be dissolved as an ion. Because it becomes a gas, it can actually leave the system. So the phosphorus and potassium that you measure in that sample should stay the same once you apply it to the land. That nitrogen, if you measure it a year before, could be a lot less. And that's the kind of calculation you have to do as a nutrient management advisor. You have to understand that. So, although this isn't part of calculating, if you're going to communicate with farmers, you should understand the different farm types and how they're storing their manure, so you understand what can happen to it, and so you can communicate better with them and understand, when you're writing up their plan, the questions to ask, where it's going to be stored, how it's going to change, and how much they're going to be able to apply. So manure management should consider production, how much is going to be produced, something you'll have to understand how to calculate. Collection, how it's stored. The storage type, whether it's liquid or solid. If it's treated, how you're going to transfer it, and how you're going to utilize it. Some farmers are going to utilize whatever they can on their land. Some won't have any land, like a no-land plan, and they'll have to ship it off the farm. Some will have more than they can use on their land, and they're going to have to ship it off the farm. So production, that calculation is going to be covered later. It's something you do have to understand for the exam. But collection, you can have solid, liquid, or semi-solid. So down where I live in Somerset County, we have a whole lot of solid. We have poultry litter bedding that comes straight out of the chicken house. It's not liquid, it's a solid. You can stack it up, you can compost it. Liquid, down here on the right, this is a hog lagoon in North Carolina. Liquid be a pure liquid lagoon, is all liquid. Semi-solid, the solids may settle to the bottom. A dairy farm is a good example of that. The solids will collect, it'll settle to the bottom, the surface will be liquid, and the bottom can be the solids. So you can have a separation of nutrients. So you have to determine the storage time so it doesn't overfill. You want to have enough storage on the farm to match the production, because you can't have it sitting outside next to a drainage ditch. You can't have it sit where it can run off. You can't have it sitting down where we're at where buzzards can get into it. So weather, the crop, the growing season, equipment, labor, and soil all have effects. The weather affects when a farmer can get out there, and we have regulations in Maryland about applying in the wintertime. So weather has an effect. The crop, what's it going to need? Is it going to need the nutrients that are in that manure every year, especially with the different rotations they have? The growing season, the equipment they have to move, transport, deposit it. All of these have a factor in how quickly, how they can move, and how they can use that. There might be treatment. It might have to be dewatered, mechanically separated, composted, agitated. Dairy farm lagoons, a good example of agitation. When they go into a dairy farm lagoon, they're going to agitate it to pull those solids up off the bottom. They don't just want the liquid. So you'd agitate and mix it. Dewatered might be something you have to do if you're sending it through specific systems. Mechanically separated, I don't see too much. Composting is something that we might do with poultry litter. A lot of farms, when you're looking at their fields, when you're talking to the farmers, when you're setting up these plans, you might notice that the fields closest to the farm have the highest, say, phosphorus content of their soils, especially where we're at down the lower shore. Before poultry litter was a commodity as a fertilizer, back in the 50s, they just wanted to get it out of the chicken house. It was most likely to be spread closest to the farm. Now, with nutrient management, you have to make sure you apply it correctly, but still there's transport costs. So the farmer might only be able to transport it so far with his equipment, with as hard as it is to get around traffic, depending on where you live, and especially if you even want to transport it out of the region. Those are all things to consider in transport. So this gets into Chapter 9. That was just a general overview of types of storage on a farm so you can communicate with farmers. But this is the kind of, these are where your questions are going to come from. This is going to have the math, and you have to understand nitrogen transformations and the different things that can happen to manure, why it's being stored, why it's being moved over time, so that when you see these questions on the exam, you can answer them. So this comes back to production. How much manure can an animal create on the farm? Well, it depends on the animal type. There is variability among species because of differences in animal diets and metabolism. There's differences within species due primarily to differences in management, bedding, and feed source, which we'll talk about. So up here among species is a cow versus a chicken. One cow versus one chicken are not going to produce the same amount of manure, and it's not going to have the same nutrient content. So there's a difference. And then within species, what they're saying here is if someone beds with sawdust versus straw, you're going to have a difference in the nutrient content and the type of manure you have. You have to understand the concept of what an animal unit is. Because one chicken and one cow aren't the same, there's a way sometimes in science we like to normalize data so we can talk about it with each other. Animal unit's one of those things. 1,000 pounds is one animal unit. So no matter what you're talking about, instead of saying one chicken versus one cow, you're saying 1,000 pounds of cow, 1,000 pounds of chickens. So that's what an animal unit is. And there's a table in Chapter 9 that has some estimates. So if one animal unit is 1 AU, then 1,400-pound Holstein is 1.4 AUs, 1.4 animal units. Here's Table 9.1. It's on page 209, Chapter 9. So in this column, you have animals per animal unit. So for every 1,000 pounds, they say you have one beef cow. Does every one beef cow weigh 1,000 pounds? No. But we have to have some way to estimate When you're running these calculations, they're not going to be exact because every animal is a little different. But we have to have some way to standardize so this can be discussed and so you can make some kind of calculation. You can't go out into somebody's farm and weigh every single animal they have. So they have tables. One animal unit of a beef cattle is 1,000 pounds. If you have a 1,000-pound beef cattle, it produces 11.5 tons of manure per year annually. So that way they know that no matter how many beef cattle you have and no matter what their difference in weight, they're saying if you have 1,000 pounds, that's how much manure is created. Same thing for all these animals. Dairy, swine, breeders, other, laying hens, pullets, broilers. So you need 250 hens to make 1,000 pounds, and they produce a similar amount of manure to beef cattle. If you went out and measured this every day, would the numbers come out the same? No. In fact, these are from 2004. This is something that probably has to be updated over time as diets change, as how we raise animals change. But this is what's in Chapter 9. Here's the kind of question, that must be the old one. Here's the kind of question you might get on the exam. They might say, how much manure on a 200-cow dairy? So you go to your table, and on a dairy, you have 0.74 animals per animal unit. You would have 15.24 tons of manure per animal unit and 200 cows. And I'd added a slide in here, but whenever you see a question like this on this exam and on any exam, the first thing you should do is pull out every single number you know you have and put the units beside it, because this will help you determine how to calculate it. You might be the smartest person in the world, you might be great at math, but when you're on a test and you're under stress and you're tired, the simple trick will help you make sure you get the answer right. So you pull out every number you know. So the question is, how much manure in a 200-cow dairy? Well, what's the first number you know? You have 200 cows. You've got to write out those units, 200 cows. Then you know that you have 0.74 dairy cows per animal unit, and you have 15.24 tons per animal unit. But your answer is in total tons of manure. So what you do is you take those units and you find where tons of manure is and you make sure that's on top. Whatever your answer is, that's the way this is flipped. If animal units was on top, you'd flip it that way. Once you have this first number, this 15.24 tons of manure per 1 AU dairy, you have to cancel units. 2 divided by 2 is 1. An animal unit of dairy divided by an animal unit of dairy is 1. It disappears. Cow divided by cow disappears. Just the unit. Like a meter over meter is 1. Kilogram over kilogram is 1. If this were flipped, if you flip this, you would multiply cows and you'd have cows squared. I'm just talking about the units, not the actual numbers. So if you write these out, you'll know the order. You know it's in tons of manure, so you write tons of manure over AU dairy. So then you take the next one and you make sure AU dairy is on top, so that cancels. And you set your cows up so they cancel. Cancel out all those units, multiply the numbers, and you'll get your answer. You can do this for almost any question on these exams. Write down what you know first. Pull out all your numbers, assign the units like a fraction, and you can calculate it. It saved me several times on exams in college. So what are factors that cause variation in the plant nutrient content of all these manures? Animals are relatively inefficient in their utilization of nutrients, and 50% can end up in their manure. Meaning, just like when you eat food, not everything is processed into your body. You're not 100% efficient. Same thing with animals. They lose some nutrients. They might want all of them. Some of it comes out. So the diet, the type of feed, affects the nutrient content. What are you feeding them? What's the nutrient content of the feed? There is species variation, swine versus bird versus cattle. Additions like phytase can help chickens retain more phosphorus. Then the bedding, and we'll talk about that in a minute. It's related to C to N ratio. And then how you store and handle that. And that mostly comes down to nitrogen loss, but you can have some loss of potassium and phosphorus. Bedding is related to C to N ratios. You should have talked about this yesterday in the soils course, in the soils part of it. But all these different, if you use these beddings, each one of them has a different C to N ratio. The more carbon you have in there, 301 means you have 300 times more carbon than nitrogen. Microbes are like us. They don't want one nutrient. If you have 300 times more carbon than nitrogen, they're going to eat all the nitrogen they can in there with the carbon, and they're going to run out of nitrogen, so they're going to stop. They need a balanced diet. So the lower your C to N ratio is in that bedding, the more they can just feed off the bedding. But if you mix manure into here, which has a lot of nitrogen, if you have the sawdust bedding, which is 300 to 1, and you add manure, which has plenty of nitrogen, they can eat all the nitrogen in the sawdust, and then they'll go after the nitrogen in the manure. So they can actually lock that up and immobilize it. So something like sawdust will lower your nitrogen content. It doesn't necessarily go anywhere. It's just immobilized inside the microbes, versus alfalfa, which has enough nitrogen itself. Now, I don't know anybody that uses alfalfa hay as a bedding. Sometimes it gets mixed into cattle barns if you're feeding it to them. More likely you're going to use straw, corn stalks, and sawdust. But this is why bedding can affect the nitrogen content. So manure nutrient content varies by species. This is table 9.2, page 209. So you can see broiler litter has 59 pounds per ton of nitrogen. As you do a lot of different nutrient management plans, you will see numbers like this vary. This is from a table in 1990. But when you come down to horse, it only has 9. Same thing with phosphorus. 63 pounds per ton of phosphorus, while horse only has 6. So this is just to reiterate that all animals don't have the same amount of nitrogen, phosphorus, potassium, even micronutrients in their manures. And that's why you have to treat each one differently. You also have other nutrients. This is a benefit of manures. It has all of these other macronutrients and micronutrients that plants need. Farmers that are able to use this over the years might not see micronutrient deficiencies. They're in such small amounts, and they're not really environmental problems in most cases, unless there's excess arsenic for some reason in a manure. You don't have to worry about these, but it's something important to remember. This is a benefit to farmers. This is something that they're getting. If a farmer can't use this for any reason, can't use manure, he might start seeing micronutrient deficiencies. As a nutrient management advisor, this is something you should remember and something you should discuss with them, something they can look for during the growing season. And these are some more of the micronutrients across different manures. So that table's in Chapter 9. Storage and handling can cause significant nutrient losses, especially nitrogen. When you're storing manure, the simplest one to think about is dilution. If you add rainfall to anything, if you add water to something, it's going to dilute it. That's one way. You can have settling. So you have that dairy lagoon. If you have settling of solids to the bottom, you have a separation. If you sample that surface liquid, it's going to have a lower phosphorus content than the bottom. So you can have a settling out of phosphorus. And then the one that you're going to be the most concerned with, the gaseous loss of nitrogen through volatilization. So you can lose that during storage. Phosphorus and potassium loss during storage are relatively low in most cases. You would probably have to have a direct loss of the manure. Maybe if you had a dried pile of litter and some of it blew off, or you had some runoff, you could lose phosphorus and potassium. They don't become a gas like nitrogen. This is why nitrogen is hard to discuss with anybody in an agronomic system. Losses of pea and lagoons can be due to the settling of solids, like we just said. So nitrogen can be lost during storage in several parts. Simply, as the animal is releasing the waste, if you have an open lot in the barn, you can have ammonia volatilization straight from the manure. If you're storing it over time, you can lose ammonia. You can also lose it as gas emissions, nitrous oxide, depending on how it's stored. You might have it reduced into N2 gas, and it can leave your system. If you don't have a very well sealed system, you could have nitrogen lost as nitrate. It can leach out. So ammonia, manure has ammonium. It can become ammonia and be lost as a gas. It has organic nitrogen, which can become ammonium and then can also turn into ammonia and be lost as a gas. That can become nitrate. It can leach out. Both of these can be picked up by microbes and immobilized. And in some systems, if you have anaerobic, if you have low oxygen, you can have it denitrified and turned into gaseous N2. This is what's important to remember, that you have two types of nitrogen in manure. You have organic and inorganic. Everything inside of your body is organic. Your living thing, the nitrogen in protein, is an organic molecule. Plants uptake ammonium and nitrate. They uptake mineral forms. If that nitrogen is still in a protein, they can't pull it in. It has to be released. It has to be mineralized. That's where that word mineralization comes from. You're turning something organic into a mineral form, which can then be uptaken by plants. So manure has some of that nitrogen still in organic form. It has some that's inorganic, that ammonium and the nitrate. So plants could take this up right away, but what you notice, this one can leach out, this one can turn into ammonia and become a gas, so you can lose these. The organic nitrogen has to be released. So this is where you have to do calculations. The most common form of inorganic nitrogen is ammonium. Here's a table, 9.6 on page 214. Of all the amounts of loss you can have in these different types of systems. So you can see in most cases, they list some losses, possible losses of phosphorus and potassium. But when you get to the actual table of calculations right here, they keep it pretty low. So for a solid system, you can lose 20 to 35% of your nitrogen in storage and handling. Liquid slurry, you can lose 15 to 30% of nitrogen. But you can see all the phosphorus and potassium levels are a lot lower, except for liquid lagoons, when you can get up to 80%. The bedding content, again, remember that C to N ratio that's going to come into this next table, can affect how much nitrogen is available. This is another table from Chapter 9 that shows how you're going to calculate nitrogen loss during storage while that manure is just sitting there not being used. How much nitrogen is lost in these different systems. So poultry manure on sawdust, your factor of nitrogen loss, you get 50%. If you have 60 pounds, you'll only have 30 in this type of storage system. And a lot of that's due to that C to N ratio of the sawdust, that high C to N. When you come down an open feedlot and storage slurry, you can lose a little less, but if you look over here at phosphorus and potassium, most of the time the number is 1. That means you're not losing any. So they're not predicting any loss if you're storing it in a pit, if you're storing it in a slurry. And over here, in these types of systems, your nitrogen is probably more likely lost as a gas. So that's why C to N, how you're storing, denitrification. You can see the phosphorus and potassium are pretty simple. Open lot or feed lot, this loss right here is saying, well, you can lose some as erosion. Potassium you could lose as leaching. But in general, these stick around where this can be lost as a gas, and it can be immobilized, it can leach out. Nitrogen is more difficult to handle, more difficult to predict. And this is a continuation of the table. There is a way they lower manure content. This is for poultry. It's a material called phytase. Cereal grains are a major feed ingredient for animals. And approximately 2/3 of the phosphorus in these grains is in the form of phytic acid or phytate, and it's poorly digested. So they figured out an additive to add phytase. It's an enzyme. It helps poultry and swine utilize more of the phosphorus. So if they utilize more, they hold more in their bodies, so there's less phosphorus in the manure. This is one way they were able to reduce the phosphorus content of chicken litter. So that's a way that you retain the phosphorus in the poultry, and it's not in the manure, so you're lowering it that way. So nitrogen forms in manure. You've got the organic nitrogen. It's bonded as a molecule. You have the inorganic, the mineral forms, ammonium and nitrate. The availability of nitrogen depends on how much and how quickly the organic will mineralize and how much you might lose of the inorganic. So the inorganic can have a large range, 20 to 65% of the nitrogen. It's immediately available to plants. They can uptake it right away. The more that you can preserve, the more is available to plants. The organic fraction has to be converted. It has to be mineralized. So over here, you can see dry poultry, 77% is organic and 23% is inorganic. So 23% would be immediately available to plants. 77% would have to be broken down and released by microbes during the growing season. So this might be one reason why people would prefer commercial fertilizers, because they would have that immediate nitrogen. You can see that all these different types and how they're stored switch on how much is organic and how much is inorganic. So the release of the organic nitrogen from manure is by microbial breakdown, the release to inorganic forms. And they have tables and calculations for this. And again, like everything else, they're as accurate as we can make them. And they do it over several years. So here's just an example of the table: cattle, layers, and horses. And this is the percent release, not remaining. The year of application, 35% of the organic nitrogen will be released that first year. So whatever's bound up in organic forms, 35% of that can be released. The second year, 18% of the original amount, and then, the year after, and then the third year, the second year after that, is 0.09. So you release most of it up front, but there's still some available for the next couple years. They're not going to be able to release it all. They release the easiest stuff for them to break down, what they can get to, but over time they can release more. That's why you would get a nitrogen credit from using manure, because all the inorganic stuff immediately available or lost. The organic, some released the first year, some released in subsequent years. This is where another question would come in. This is where you have to understand the different types of nitrogen, the different types of manure, because they might ask you what type of manure, how it was stored, how much organic nitrogen does it contain, and what is the mineralization rate. You might have a very simple question, or you might have one that's complex that asks you several stages. So you'd have to understand that you can lose nitrogen during storage, you can lose nitrogen during application. So a simple question might be, how much nitrogen is remaining in a sawdust and poultry layer after 0, 1, and 2 years in the soil? So you go to all those tables. You pull out the amount of total nitrogen in the layers. It's table 9.2, page 209. It's 59 pounds per ton. The storage factor for poultry and sawdust, table 9.7, page 215. It's 0.5. Then the amount of organic nitrogen in dry poultry, 77%. Of that is organic. So 77% has to be mineralized. And then you'd have mineralization rates for each year, 0, 1, and 2. You could set up a simple table. What you'll notice, though, is the total amount of nitrogen, the total amount that's organic, and how you storage, those numbers aren't going to change. What's changing over time, 0, 1, and 2, is how much it mineralizes. So the nitrogen released in year 0 is 13.6, and in year 2 you get 1.8. So there still is some nitrogen released. That could be a more complex question where you have to look at several tables. If they give you those tables, you'd have to look up how it was stored, what was the bedding, what's the mineralization rate, what year are they asking me. You might also get a very simple question where they just say, you have this much organic nitrogen, in what year, how much is released, and you just have to look up the mineralization rate. So as long as you understand organic versus inorganic nitrogen, you understand that animals have different amounts of nitrogen, and that how much is released over time changes, you can look those up. Just remember to read the questions carefully so you find the right values. There's also what they call plant available nitrogen. So what we just covered was how much is mineralized. There can be a broader question, how much total nitrogen is available? There's going to be what can be mineralized or released, but there's also, remember, that inorganic that's immediately available. So plant available nitrogen is a way to, you just combine the inorganic nitrogen with that organic nitrogen. So volatilization is a loss of nitrogen as ammonia gas. There are two major pathways for this loss. Conversion of ammonium N to ammonia, the conversion of urea to ammonia. So these nitrogen forms in manure, they can become gas. They're inorganic, they're available to plants, but they can be lost as a gas. Urease is the enzyme that can convert urea. So the plant available nitrogen is the available ammonium nitrogen and the available organic nitrogen. The available ammonium is ammonium N times the conservation factor versus the available organic, which is organic N times the mineralization. So in this case, your inorganic can be lost as a gas, so you want to know how much have you conserved, have you prevented from being lost. Where mineralization is about a release, how much of that bound up organic nitrogen was released. So plant available nitrogen is adding how can you prevent loss of ammonium, and how much is released as organic nitrogen, as mineralized nitrogen. The equation is pretty simple. It would be that ammonium times the conservation factor plus the organic nitrogen times mineralization. This is the calculation we just covered. So you might ask you year 0, 1, or 2. When it comes to ammonium conservation, there is a different table. This is the mineralization table we just looked at. But ammonium conservation depends on, can you get it into the soil to prevent it from becoming a gas, going off as a gas? So if you can incorporate that manure within an hour, this is about application. You incorporate it within an hour in conservation tillage, 96% of that ammonium should be conserved. If it takes them 2 to 3 days, half of that could become a gas and be lost. In no-till systems where you're not going to incorporate, only 35% might be remaining. So this table is for inorganic nitrogen, about how much you can conserve through the practices you're doing, versus mineralization, which is about the release of organic nitrogen. So you might get a question like this. Lab test shows that cow manure has 16 pounds per ton organic nitrogen and 12 pounds per ton ammonium. Field is under conservation tillage and manure is injected within 6 to 12 hours. So they give you all these variables. You go and look at your table. 12 pounds per ton times 0.53. That's your mineralization rate. That's how much is released. 16 pounds per ton times 0.35. That's how much is conserved. Add that together. You have your plant available nitrogen. So this lets you know how much nitrogen from this manure is going to be available to the plant this growing season. And then after that, if it's not enough for the crop, then you make the recommendations to supplement with conventional fertilizer. So plant available nitrogen is the conservation of ammonium and the addition of anything released from organic nitrogen. Another thing you have to understand is once you know how much nitrogen is in there, how much is going to be available to the plant, then you have to calculate an application rate, because everybody's going to have different equipment to apply their manure. It might be in a different state of repair. Some might be older, some might be newer, some might have GPS. Some are going to be better than others. But they have to be calibrated, because the whole purpose of doing all this nutrient management is to make sure you apply the nutrients you need and not any in excess. So if you underapply, you don't have enough plant nutrients. If you overapply, you cause environmental problems. So you also have to do calibration of these manure spreaders. So there's different types of spreading equipment. You have broadcast applications of fertilizer, manure, and lime seed. You can broadcast them. It has even distribution of crop inputs. If the machine's working correctly, it should spread it evenly across the surface. Your accuracy depends on the ground-driven conveyors, the width of the spread, visual reference, compass, strips, crop rows, or wheel turning techniques, how wide it's going to go, how fast you have that PTO running. To calibrate and adjust these, you have to pay close attention to the operator's manual. You set the machine for field conditions. And like any piece of farm equipment, if it's not working right, you stop immediately and fix it. You don't keep going. If the outcome is not desirable, stop and readjust. Don't keep going. You want to get it right. Machinery may require added attachments for proper jobbing. So calibrating manure application equipment. Proper calibration is a critical part of manure nutrient management. You can do it in one of three ways. And this is if you're broadcasting or spreading. There's the tarp method. You place a tarp flat on the field. You spread manure on that tarp. You have the area with a tarp covered. You weigh the manure that was collected on that tarp, and you can get an application rate. Because you know your nitrogen content, but you have to know how much are you applying through that spreader to the land to get it to a per acre basis. There's a swath and distance method where you pretty much run that manure spreader out. You measure the distance traveled, the width of that swath, the total amount of manure in that spreader, and you have the amount you applied that way. And then there's the loads per field method. You know the acreage of your field. You calculate how many loads it took you to spread that, and you divide by the number of acres. There's an obvious problem with that. If you're wrong by the time you're done, you did the wrong application rate. You have to, there's a lot of variables in agriculture. You have to keep all these variables straight. Equipment speed, gate settings, type, and consistency of manure have to remain constant. If you change any of that, if you drive faster over one field than another, you've changed your application rate. You change your gate settings. If your manure is wetter or drier, easier to fling, it can change how much is applied to the land. So the tarp method consists of placing a tarp or a plastic sheet on the ground. You use the manure spreader, drive across, spread it at the rate you're applying. You want to go the speed you're going to go, have the gate settings the way they're going to be, drive over top, spread it out. Weigh and collect it. Might have to have a decent scale for this. And you'll know the amount that's being applied per acre. Do it 3 times. You're not going to get it right the first time. You need a good average. So you do something like this 3 times. They have conversion factors. If you have certain tarp dimensions, they can go ahead and convert by pounds of waste. They have a quick table for you. You can't do it by hand, which I usually suggest doing it by hand. But they have a quick table where you convert. If you had 10 pounds of waste on a 6 by 6 foot tarp, you had 6.05 tons per acre applied. So they have a quick table, a lookup table. But you can also do the calculation. If you have an 8 by 8 foot tarp and you collect 8.8 pounds of manure, 8.8 pounds over 64 square feet. That's the square feet of the tarp. And then you multiply by 21.78, and that will turn it into tons per acre. That's a quick calculation, a quick conversion. And then there's the swath and distance method. You determine the weight of a load of manure either through by direct measurement. Somehow you weigh the entire manure spreader if you have a scale big enough, or you can convert a volume measurement. Some farmers I know, they use the bucket method. They weigh a bucket of manure and then they calculate the volume of that bucket and then apply it to the volume of their manure spreader. But some of them have odd-shaped manure spreaders. So you have to understand the full volume, and if you overfill that, you pile over the top, then you would not be correct. It would have to be an even amount. So determine the width of the application of the swath. How far did you spread across that field? How long was that application? With a full load and manure spreader, you can have a good calculation. You have a spreader that holds 7,000 pounds. You run that entire 7,000 pounds of manure over a 35-foot wide, over 1,200 feet. Same thing, calculate it out into pounds per square feet, multiply by 21.78, and you have tons per acre. So that's the swath and distance. The tarp, just one little area, swath and distance, the whole manure spreader. Loads per field method is the easiest to calculate because you just keep going. You have to know the weight in tons of a load of manure. You have to make sure that each load would be the same amount. Determine the size of the field in acres. Count the number of loads applied to the field. Multiply that number by the weight in tons of a single load. And divide that number by the acreage of the field. The problem with this method is, by the time you get done doing that, if you were wrong, if you over-applied, you put too much nitrogen out. If you under-applied, you're going to have to make it up. The reason you'd want to, even though the tarp might be a little harder, the swath and distance might take a little more work, and this seems easier, you're more likely, if you do it over a 20-acre field, then you don't know until the end that you might have been wrong and that you weren't calibrated correctly. So this is just about that major drawback. It's an after-the-fact calculation so that the applicator does not have the opportunity to make adjustments in the application rate to that particular field. And it may best be used as a method of monitoring application rates during a clean-out of a storage facility. But you would still use the first two methods, the tarp method or the swath and distance, to actually calibrate the spreader.